Okay, so I think it's slightly different. I mean, this is good. I basically take the limit of the Picard iteration.
No, you took the limit of that thing.
Yeah, I took the limit of the defining equation.
Yeah.
And then.
But I mean, same thing, yeah.
And so that the fact that it satisfies that thing with there being no distinction between the n and the n plus 1, that is then, by the fundamental theorem of calculus, gives me that dy star d zeta.
Yeah, you still got the
Yeah.
punchline.
And then, so the uniqueness finally is down here. If you, usually uniqueness, you assume you have two things and then show they're equal.
Mm-hmm.
So I suppose I have a y star star, which also satisfies the initial conditions. And then I use the lemma to look at the difference of y star star and y star star, y star.
Mm-hmm.
And, upsilon, look at that. Moreover, upsilon equal to the supremum of that provides a bound for that on that. And, 36. So eventually I found a bound on the difference between y star star and y star, which is upsilon L to the n plus 1 z minus z naught to the n over n factorial. And the thing is,
what's an exponential equation?
In a game of things like on the numerator versus factorial, the factorial wins. Because as n goes to infinity, that in equation 36 goes to 0. So you can make the difference between the star and the star star solution as small as you like, so therefore it follows that they're equal. And that's the theorem. I think this took me about 3 weeks to come up with this. Like it was.
Why does that equation look so similar to the exponential though? Is that just like a thing?
The n factorial?
Yeah.
I don't know where that is there. I mean,
it's
I
like,
guess.
You know, if you change out that L for a -1, I mean, it's exactly what you wrote.
You could. I think you could look at that as like a term in the exponential, so it's like bounded by. But that's not anyway.
Yeah.
All right. So again, this was somewhat similar to the proof in Nagel, Saff, and Snyder, but I had to modify it considerably, and I thought I was going to get stuck a couple days, but then you know, something shook. I was very excited when I finally got this done. Summer 16. Should really have this thing published by now. Good grief. Anyway.
How does the publishing process even work?
Don't ask me. You should find a journal with people working on things like you're working on, where you can get reviewed by people who are interested in the same things you are, and don't have some political axe to grind against you. And you can do all those things, then you send it to that journal, and they go, hey, this is like the stuff I'm doing. And it looks mostly right. Publish! Or some people are super picky, and they're like, you haven't capitalized Cartesian. How dare you fix this? And so you can run into, reviewers of every sort and fashion. But I think more often than not, the what you run into these days is like people just don't read it. They just kind of like glance over and like, But ideally, we should all be reviewing each other's papers carefully and like giving constructive criticism about this calculation goes sideways. Now, I have reviewed some papers like that for people where every time I find something that's wrong, it turns out like, no, it's just they've skipped a half-page calculation which I'm showing you. I mean, there are very, very careful papers out there. It's just there are also a lot of papers that are full of errors and have been reviewed. Papers are written by humans and reviewed by humans, so they have errors. But, thankfully in mathematics we do have, I think the main thing that separates mathematics from so many other things is like definitions. And there is an expectation that you're saying something that's objectively true, right? So like it's math.
Yeah.
But
there's more concreteness in that.
Yes. So theorem 3.3 is a kth order differential operator. All right.
Big school.
And so D is d dz. Right? So I'm looking at a kth order AODE, L of y equal to g with initial conditions. All right.
Mm-hmm.
Then I say that that has a unique solution. So.
Yeah, this looks like something from DE.
Mm-hmm. So did you see that you can take a? Well, you didn't do systems, did you?
I think we did. Systems of differential. Like,
Did you talk about how any? Did you talk about how any kth order differential equation can be rewritten as k first order differential equations?
not sure.
Oh. Well, that's really all that's going on
Is
here.
it just n minus 1?
I'll show you an example. So suppose we have, you know, y prime plus 3y prime minus 2y prime plus y equals 0. That equals to t. There you go.
Yeah.
This is a third order ODE. So we can make the following substitution. X1 equal to y,
Yeah.
x2 equal to y prime, x3 equal to y prime prime. And with that substitution, which is known as reduction of order, all right, let's see what happens. So first of all, we have x1 prime is y prime, right?
Mm-hmm.
Which is x2. Did I ever hit record?
I think so.
Yeah, I did. Yeah, I did. Now, what's x2 prime? Y prime, right?
Mm-hmm.
But more to the point, it's x3. What is x3 prime? It is y prime, which is, by the way, minus 3y prime plus 2y prime plus or minus y plus t, right?
Mm-hmm.
So x3 prime is, in fact, minus x1 plus 2x2 minus 3x3.
So you solve that one and you plug it in.
So the moral of the story here is I've taken this single first order differential, third order.
Yeah. And you made it a second order.
Yeah, well, worse. I've made it this system of three coupled first order differential equations.
Okay.
You can always do this. If you have a kth order linear ODE,
Mm-hmm.
you can rewrite it as a system of k first order ODEs by making this substitution. So technically speaking, theoretically speaking, if you don't want to think about the kth order problem, you don't have to. Like, you can always look at k first order problems which are coupled rather than one kth order problem. And then, yeah, I mean, you solve this, then you gotta kind of go back to just to give you a kind of a flavor of how these things go. Here's one you're familiar with, right?
So I would change y to x1. And then x1 prime is x2. Yeah.
Right, so x1 prime equals to x2. And
x2 prime equal to x3.
Yeah, x2 prime is y prime, which is minus by prime minus cy divided by a.
Mm-hmm.
So we have minus c over a, x1, minus b over a, x2. So if you look at this as a matrix problem, So you remember the characteristic equation here was like AR squared plus BR plus C equals to 0. You guys use R?
Yeah.
You should use lambda. But so this one here, what's the characteristic equation of this 2 by 2 matrix? Right, determinant of matrix minus lambda, if you like.
Okay.
Or lambda minus the matrix, I'll be minus lambda plus the. So here's that characteristic equation I was talking about the other day.
Okay.
The solution to this will give you the eigenvalues of the matrix, right?
Yeah.
So multiply that, I get myself a lambda squared. Did something wrong?
No, you should pull out the you're trying to pull out the quadratic, right?
I'm just trying to take the determinant. So this is,
lambda squared times lambda BA.
Yeah, minus B over A lambda, right?
Yeah.
Minus C over, or plus C over A, right?
Yeah. Ooh.
And this should have been a plus, shouldn't it? Because minus
Yeah, I was
minus.
about to say, yeah.
So it's that, right?
Uh-huh.
So that's really 1 over A times A lambda squared plus B lambda plus C.
Mm-hmm. Which is your characteristic equation. But where's oh yeah, but you got the A from the X, you got.
So what I'm getting at here is that this notion of characteristic equation, right, is pretty far divorced from that eigenvector equation. But it is the same algebra. To solve this system, you can find eigenvectors of the matrix, and then e to the eigenvalue times eigenvector gives you a solution to this. And when you look at those, they go back into the exponentials that you usually find over here. But anyway, 3.3 is it's just reduction of order. So I'm saying you can take a kth order problem and you can do reduction. Reduction of order still works over the algebra is my point.
That's good.
In fact, there is and this, by the way, is called the complementary matrix of the system. All right, so the complementary matrix of the kth order system, it's got, a matrix with superdiagonal ones for the first k minus 1 rows, and then minus the coefficients of the differential equation on the last row, assuming it's a constant coefficient differential equation, as I do here. And so the point is that as we look at it, we've got the F, quote unquote, of the existence and uniqueness theorem is this matrix A times the vector W, which is the W here have the interpretation of being the reducing variables as it happens, but the point is that the F is AW plus B, right? So that is a differentiable because, and basically the size of the matrix A bounds the size of the partial derivatives. So we've met the conditions of the existence and uniqueness theorem, therefore there is a unique solution. And once you know that, well, next you have to talk about what do we mean by independent solutions. And so here I start to get fussy. If we have a connected subset of the algebra, and we have functions to the algebra, all right, from that connected set, then we say the set of functions f1 through fm are linearly independent if and only if the trivial equation forces trivial constants. See that the linear combination c1f1 plus c2f2 plus to cmfm equal to 0. Conversely, if the f1 through fm are not linearly independent, they're said to be linearly dependent. It is important that I take the definition of linear independence here to be this, and not to be what's oftentimes taken in linear algebra. Linear dependence is when you can write one vector as a linear combination to the other ones. That does not work in our context. It is possible for two vectors over an algebra to not be linear combinations of one another, and yet be such that you can take linear combinations of them equal to 0, such the coefficients are not 0. Linear dependence is no longer captured by the statement that you can write one of the vectors as linear combination of the others. We lose that over a ring. The zero divisors allow us to have non-zero vectors whose linear combination is equal to 0 despite it not being the trivial combination.
That just makes things a lot more tricky though.
It does. So like over Z6, for example, we could have stuff like 2 times, 3 comma 0 plus 3 times 0 comma 2.
Yeah.
Well, that's 0 because this is 0 and that's 0.
Yeah.
And yet certainly there's no way you can write 3, 0 as a multiple of 0, 2.
Yeah.
So these are linearly dependent over Z6. Yeah. And you can play the same game over like the hyperbolic numbers using 1 plus j, 1 minus j. It's not about Z6, it's just for convenience. Convenience of jibber jabbering. So, but anyway, there's linear independence. So that was it. For you and me here, that was a pleasant half-minute conversation. That issue has wasted at least a month of effort with other students because it was like we didn't understand that's what the problem was, but we had this fundamental going back and forth with linear independence is when you can write one thing as a combination of the others, versus linear dependence is when linear combination being trivial forces it to be the trivial combination. So that's it.
Yeah, you're saying that like if we combine them to equal 0, that means it has to be the trivial.
Right.
So
Equating the equivalence of these two concepts is not true over a ring. And like that's what it took me a while to like free myself, because in the linear algebra over a field, you can freely interchange these two ideas.
Yeah.
It's okay. Zero divisors, they mess it up.
But if there's only if the algebra only has one zero divisor though, that would hold.
There's always infinitely many. There always has to be a cofactor for it to be an interesting zero divisor. And they always come in lines, at least lines. Because the scalar multiple of the zero divisor is still a zero divisor. They're a cancer that grows at least along a line.
Yeah, I didn't even think about that. I forgot that like if you take r cross r, like there's no line, it's just 0 because 0 kills everything. So you only get like the origin, right?
And they're funkier still, right? Because they, in terms of like manifold dimension, you can have like the H3 has that like plane of zero divisors.
Yeah.
And it's also got that line
of
zero divisors.
Mm-hmm.
And so definition 3.5. Do you guys talk about the Wronskian?
No, not in DE.
Oh. The Wronskian is...
Oh yeah, we didn't talk about matrices in DE.
But you don't have to talk about, well, a lot of people will talk about Wronskians and DEs and not talk about systems. The Wronskian is very helpful to analyze the linear independence of functions.
I never heard that, the Wronskian though.
Oh, well let me talk to you about the Wronskian for a bit.
Owen, come, it's time.
So, suppose you have linearly independent functions y1 through yn.
Mm-hmm.
On some subset I. So you've got c1 y1 plus c2 y2 cn yn equal to 0. Suppose you have that, right?
Mm-hmm.
If they're linearly independent, that implies what? That implies C1
Yeah,
through Cn has to be 0, right?
Wait, Cn, C0, what, say again?
If these are linearly independent, this implies, you know, C1 equals C2 equals Cn equals to 0. Okay?
Okay.
Fine. Now, this being equal to 0, beware what that means. That's an equation of functions. So this is, there's something omitted here. This is for all z and I, for example. Or if you want me to go back, we could do real and differential equations if you prefer. Does it matter?
I prefer real, but it's okay. Yeah.
We can do real. So for all t in the interval I, all right? Subject r, there we go. The story will not change. So, great. This is a function equation. Like I could put it of t, of t, of t. So what that means is if these functions are differentiable, and we're usually assuming they are, we can differentiate it. And we get c1, y1 prime, plus c2, y2 prime,
Yep.
plus cn, yn prime equals to 0. Having done it once, we can keep doing it
Yeah.
all the way to the n minus 1th time. I mean, you could keep doing it past that if you wanted to, nothing's stopping you. But I'm just going to do it n minus 1 times. The reason for that is that at that point, I can take all of this and I can rewrite it as a matrix. The first row being y1, yn, the second row, and so forth. N by n matrix. But notice something about this matrix.
Wait, it's not n by m.
It is.
Well, you're doing n minus 1 though.
Ah, but the first is the 0th derivative.
Oh.
So it's all that matrix times C1, C2,
Yeah, constant.
Cn equal to 0.
Yep.
But remember, we're assuming linearly independent. Unique solution of 0. What's linear algebra say? You've got a homogeneous equation. Fix any t.
Yeah.
For any t. This is, you know, technically this is of t, right?
Yeah.
So for any of those choices of t and I,
Mm-hmm.
where you can differentiate and form this matrix, the only solution to this homogeneous problem is c equal to 0.
Okay.
Therefore, for all such t, this is an invertible matrix. So the determinant of that matrix, I'll put the t in here explicitly. It's not equal to 0. And this is what's called Wronskian of functions y1, y2,
Is
that
it whatever the
y n
determinant equals?
at time t. It's the determinant of this n by n matrix of the functions and their n minus 1th derivatives.
Okay.
This is the Wronskian. Linear independence on a set implies the Wronskian is non-vanishing on that set.
Yeah.
I don't want to walk.
A common confusion held even by some research mathematicians is that if the Wronskian is 0, then that means that the functions are not linearly independent. In other words, that if the Wronskian is 0, that forces linear dependence of the functions.
No. Because you think, yeah, because you could still have a linear dependent with that 0. Because it just has to be invertible for it to be linear dependent, right?
Right, well, the thing is, the converse is like that naive converse is not true. You can have functions which are linearly independent and yet have vanishing Wronskian. The example I can think of is this. So this x times absolute value of x is once differentiable, but not twice.
Mhm.
So Wronskian of y1, y2 at x is determinate.
Oh, x squared, 2x.
Yeah, 2x squared absolute of x minus, I should have had a 2 here. Alright.
Wait for you to derivative of y1. Why do you have a 2?
Oh, well, because y1 is, it's x squared if x is greater than 0, and it's minus x squared if x is less than 0.
No.
It's 2 absolute value of x. So that's really the issue here, is that there is it's subtle. If you were just to focus on, if our context was just positive numbers, these would be linearly dependent functions. If our focus was just negative numbers, they would be linearly dependent functions. But if we look at the context of the whole real number system, these are linearly independent functions, because you can't write y1 as a linear combination of y2. I mean, they are, it's the case-wise defining this here. Okay, so it would be nice if we could just throw functions into a Wronskian and see they're 0 and go, aha, linear dependent.
Yeah.
No. However, if we throw our functions into a Wronskian and we get non-zero, we can say linearly independent. So it works one way, but not the other. However, in the context of solution sets to differential equations, if the Wronskian is 0 for a solution set to a nth order differential equations, if the Wronskian of n functions is 0 for the solution set of an nth order differential equation, then that proves linear dependence. Something beautiful happens for solution sets that allows this naive converse to be true. But it's even more exotic than that. If the Wronskian vanishes for even 1 point for a pair of solutions to like a second order problem, that means that that pair of solutions is linearly dependent. So, I mean, I can give you linearly dependent things that have Wronskians which are 0, but the interesting example is already here.
Yeah.
This is the interesting thing, is that this is not, so what I'm really telling you is there is no second order differential equation which takes y1 and y2 as a solution set. It's one of the things I'm saying. If you believe what I'm telling you. But what's more interesting is, go on here. So see this right here, theorem 3.6. You have m solutions which release m minus 1 times a differentiable. And the Wronskian, see that, is not non-zero. See, non-zero has to be replaced with a unit.
A unit?
A unit. See, if the Wronskian is a 0 divisor,
then, so like when you take the determinant, it pops up one of the 0 divisors, so like you take this.
so here's this example I can give you.
So, yeah.
How about
I have an idea.
Okay. I'm going to try to show you a couple of functions.
I was thinking something in the hyperbolic, and then you take the determinant up and you get like a y, or 1 minus j or something.
Right. Let's see here. How about e to the 1 plus j z and e to the 1 minus j z. I think those might be linearly dependent. Well, certainly if I do 1 plus j times e to the 1 plus j z. I could probably just do 1 plus j times e to the z. I'll just keep it simpler, and 1 minus j e to the z, right? So like that'd be my y1.
Yep.
That'd be my y2.
Differentiate, it would be z. Yeah.
Maybe that's why I wanted to put the z up, the j up there. I don't know. So then, I'm not sure this is the example I want. I'm just trying something, okay?
Yeah.
Yeah, that's just 0, because this times that is 0, and this times that is 0. This is not the example I'm looking for. Try that again. How about maybe if I do this. This should do it. So then, if that's y1, and that's y2, then y1 prime.
1 plus j, 1 plus jz.
Right, I'm gonna write it this way.
Yeah.
See, I'm just being lazy. So then, see what you got. You got yourself, y1, y2, y1 times 1 plus j, y2 times 1 minus j. So that gives us 1 minus j times y1, y2, minus 1 plus j times y1, y2, which is what? The ones cancel, and what do we got? Oh. Well, that wasn't that's no good. Minus 2j by 1 y2. Oh man. See, that is an element of the units, because j's, this is invertible. This is the product, the exponentials are in the units. Product of units is a unit. This is not, these are actually linearly independent, because the Wronskian is a unit.
Yeah. That's what you said. Put there.
Dang it.
Looking for something to determine that gets you 1 plus j. Why don't you just start with the determinant and
So
work
you're
backwards?
I want to put y1, y2, y1 prime, y2 prime, determinant equal to 1 plus j times stuff.
Yeah. Minus j 0, and then some function 1. Well, what's our z? Is our variable?
Yeah, use z for variables.
Y1 equals z, and then y2 is equal to minus j.
But then y2 prime is 0,
Mm-hmm.
and y1 prime is 1. That might work. So you got the determinant of, what was it, z minus j 1, 0. Very good. So that is, oh, that's just j.
Rats. You know,
But I like your style. I take your j and raise you a j plus 1.
that's what I was gonna.
Yeah, but thank you. I'm sure you're about to that. Let's see here. So there we go. Yeah.
So that's a zero divisor. That means those two equations are linear.
Yeah. And in fact, you can see here lemma.
Yeah.
Any function. J plus 1.
Yep.
Has the Wronskian of the Wronskian of these two things.
Makes sense because one's a linear dependent. One's linear independent for everything.
It's going to be in the, so yeah. Now, okay, so the Wronskian's a zero divisor. I mean, my claim to you is that means it's linearly dependent.
Yeah.
Here's how that happens for this one. For the z and the j plus 1. So let's see here.
You can.
Oh man, how does that happen?
JZ. No. You need something. So JZ minus.
I want like c1y1 plus c2y2 equal to 0, and yet that does not imply.
C's have to be 0.
The c's have to be 0, right?
Wait, no, that's linear independent, right?
Oh, okay, so I can do 0
Yeah.
times y1 plus
Really, any constant.
j minus 1 times j plus 1.
Yeah.
That's 0, and yet c2 equal to j minus 1, not equal to 0. And that's it. You can pick the cofactor of the zero divisor, the null factor if you like, and that's where the magic is.
Yeah.
So, if the Wronskian is a unit, you get linear independence. Now, I say in practice, we are primarily interested in solution sets to linear nth order AODEs. All right. Where the study of linear independence is greatly simplified by Abel's formula or Abel's formula. That's the same as like abelian, and so forth. In particular, this formula forces the Wronskian of a full solution set to remain in either the units or the zero divisors. It can't be one. It's gotta pick one and stay there for an entire connected subset. And here it is. So if you have continuous functions on a connected set where the zeroth function is in the units, that condition that the zeroth functions is the units, that's what I mean by a non-degenerate nth order AOD. That assumes that the leading coefficient is not a zero divisor. And it doesn't take values in the zero divisors over the domain. Okay. So if you have that a0 y to the n plus da 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 plus a n y equal to 0, then the Wronskian of y1 through yn is equal to some constant times the exponential of the integral of the ratio of the first and the zeroth components as so defined. And actually I should probably have a star there because I do mean the integral over the algebra.
For the theorem 3.7?
Yeah.
Oh, that looks like the integrated factor.
Mm-hmm. Now,
have you proven that in algebra? Sorry, Captain's in me.
the what?
Like, is that be like one of the questions that like we try to like see if you can have an integrating factor maybe like over hyperbolics or something?
Oh yeah, that's in here.
Okay.
Yeah, we're in there.
Ooh,
This is at the moment just like the general theory. So
mm-hmm.
Abel's formula is often proved for like n equals to 2 in your ordinary differential equations course.
Yeah.
What follows is the proof that this works for n
Okay.
on the next page, and essentially what I there have is the formula for the Wronskian using the Levi-Civita symbol. And when we differentiate, it's actually kind of the same calculus we're just using for the n Pythagorean theorem,
Mm-hmm.
the n-fold product rule.
Yeah.
So I get rid of everything except for that one term remains in w prime in equation 43. And then I replace the nth derivative with the appropriate linear combination of the lower order derivatives, like in the reduction of order. So equation 44 is the reduction of order step, kind of. And there's why we need to be able to divide by a sub naught. It needs to be a unit, otherwise we're in trouble. And of course, when you plug that in for the nth derivative, almost always you have a repeated column in these things, with the sole exception of the leading coefficient, the a1 over a naught term in equation 45. Only that first term is non-trivial, because otherwise all of the other things, there's either the repeat of the first or the second or the third or the fourth, some other column in those coming from when you collapse them into the epsilon symbol, look at the determinant that corresponds to the determinant of a matrix with a repeated column. So the only thing I actually need to worry about in all that mess is just the a1 over a naught.
Yeah.
Which I think I finally get to the point of it at star, right? That star
Mm-hmm.
equation. All right. But what is that? Well, that's the Wronskian again.
Yep.
So we have minus a1 over a naught times Wronskian. So you have derivative equals to minus a1 over a naught times Wronskian.
That's cool.
So you can integrate both sides, and that's what gets you the handy dandy formula there.
That's nice.
Yeah. And so this I lifted. See, this is in my differential equations notes because this is the sort of thing I do in differential equations. Not that I force the students to do it. It's just something I had already worked this out for my differential equations course when I got to this research. This is not something worked out for this.
Mm-hmm.
It's something I just changed real derivatives to algebra derivatives and said, oh, it still works. And I was prompted to do this because my brother made he's like, oh, the Wronskian's what's general. And I was like, what do you mean? And he's like, what's Wronskian's general? And I was like, is it? And then I went out to calculate it, And yeah, the Wronskian is very, very general in its application. And this Abel's formula, so there you go. I mean, once you have that formula, think about it. The exponential is a unit.
Yep.
You can calculate that integral.
Mm-hmm.
So that's just whatever that is, it is.
Yeah, it's just a real.
And so it all comes down to what C is. If C is a unit, the Wronskian's in the units. If C is a zero divisor, the Wronskian's in the zero divisors. That's all there is to it. And so this is incredibly useful as we're studying solution sets to differential equations. If I have some doubt about solutions I'm constructing actually forming a solution set or not.
Mm-hmm.
So the fundamental solution set, it should be, for an nth order problem, it should be n solutions
Mm-hmm.
that are also independent in the sense of linear independence over the algebra. That's what I need. So if I can look at the Wronskian of them and prove for whatever reason that it's a unit, if the solution in the Wronskian is non-zero, I got a solution set. And
If it is a zero divisor, that means your solutions have to be zero divisors.
that means that I don't have a solution set. It means something, I've got two versions of the same thing in some sense or another. Or I could just, maybe I'm in the context where there isn't a, when we look at degenerate differential equations, you can either lose existence or uniqueness.
Oh, okay.
Or there's a lot of things that can happen for the degenerate ODEs. But corollary 3.8, what's it say? Let me get my coffee. I don't know why I keep talking about the coffee. What's wrong with me?
It's probably cold again.
I know. This always happens. See if any bugs floated to the top. Stupid bugs. You know what it is? It's bananas. Sometimes I'll do that like 3 times.
Yeah.
So I think the next corollary is
3.9, 3.8, hold on.
But yeah, corollary 3.8 just says what I've already said, which is that we can use the Wronskian, if the Wronskian is a unit, the functions involved are linearly independent.
Yeah.
If the functions are a solution set, and the Wronskian
It's not a zero divisor.
not a zero divisor, it's
Looks
a
good.
solution set, right? But it's more than that. Like, notice that if it's a solution set, okay, so like if it's divorce yourself from the solution set.
Okay.
You would need that the Wronskian is non-zero.
So it says like, when you take a
Oh, my brain works.
wait, so if you're trying to solve, we're talking about a system now, like since we're dealing with the Wronskian, we have to be talking about a system, right? Can you just take one?
Well, I'm
Well, like,
talking,
we can always make the system because if you have the K order.
yeah, I'm talking about the nth order problem, but it corresponds to system.
Yeah. So this, so whatever differential equation you have, why don't you take the Wronskian of it first before trying to see if it has a solution set?
Well, I don't know what this. I mean, I gotta find the solution set before I can take the Wronskian, right? Like, how do you find the solution set for a given differential equation?
Well, that's not. Is that a? Well, yeah, I guess it would be because
I mean, excuse me, you're not wrong because you're like, you should respond to me. You just gave me a formula for the Wronskian
yeah.
in terms of the integral of the coefficients. You can calculate the Wronskian. Man, that formula's weird. So what's so interesting about that formula is it gives you a formula for the Wronskian independent of y1 through yn. It just depends on the integral, the ratio of the coefficients to the differential equation itself. And yet, the direct computation of the Wronskian definitely involves the wy through the y1 through yn in the differential.
Wait, so yeah, if you can find the Wronskian before you do differential equation on it, and so you should be able to see if it has a solution set, right?
I don't know. I think, as far as I can tell, corollary 3.8 is just saying what I already said, and I'm just repeating myself. But I don't know what. I mean, if I calculate the Wronskian for a differential equation, how does that help me find the solution set?
If it's a zero divisor, you know there's none. But C
Oh.
is equal to 0.
But how do you pick C? See, that's the thing. How do you pick the C? Where does C come from in that formula, Abel's formula, you know? See, I guess right there is where it connects with the y1 through the yn. Like, that's going to, if they're actually linearly independent, C is going to be a unit, whereas if they're actually linearly dependent, then that C is going to have to be a zero divisor. But ironically, the z dependence is all tied up in that exponential of the integral of the ratio. Like that's the only possible kind of z dependence the Wronskian can have, is that particular multi-formula.
In your subnote, if I was formed by several connected components, then we would have different values for c in different components.
Yeah.
Oh, could you choose c such that, we know that, right? That c0 with the Wronskian.
If all the coefficients
Yeah.
are 0, then
So if you have a but no, because you can have a Wronskian equal to 0, that's not.
I remember small victories.
Yeah, because we proved that just because you're Wronskian 0 doesn't mean that
I would
you're.
offer you an Oreo, but I already know.
Okay. Wronskian. So. Yeah, we said that if the Wronskian equals 0, that doesn't necessarily mean that they're not independent, right?
Right.
Yeah, we can't pick C.
Except when there are solution set.
Yeah, but
So
if we only have the equations, we can't say. I was trying to say, like, with that equation, we should be able to find whether or not.
that equation is only good for solution sets.
Exactly,
Like that,
yeah.
you have to have the y1 through yn are solving that given differential equation, which has within it the coefficient a0 for the leading derivative term
Yeah.
and a1 for the next leading term. So, now definition 3.9, I think I told you already, fundamental solution set for an nth order linear differential equation means that the functions in the set are solutions to the differential equation and they're linearly independent. Now that's important because theorem 3.10 says if you have an nth order linear differential equation with continuous coefficient functions, all right, on a connected subset of the algebra, then there exists a fundamental solution set. How do I know that there exists a fundamental solution set? I apply theorem 3.3 n times. And 3.3 is the existence and uniqueness theorem that kind of had to work out. And I choose solutions such that the initial conditions have like the jth derivative 1 and everything else 0. So this is an nth order problem, so the initial conditions I can choose so that like just one of all of the derivatives is 1 and the rest are 0. Like it's kind of like what we were looking at with the sine and cosine, the defining sine and cosine in terms of like the initial value problem with cosine having the function evaluated at 0 be 1, the derivative evaluated at 0 be 0. This is kind of using that same kind of thinking. But the point is, by the existence and uniqueness theorem, I can find those n solutions with those that solve those n distinct initial value problems. When I look at the Wronskian, what happens when you evaluate the Wronskian? But all those initial values, they're all at the same z0. So when I plug in z0 into the Wronskian, I get 1, 0, 0, 0, 0 for the first column. I get 0, 1, 0, 0, 0 for the second column.
You get diagonal ones.
Exactly, I get the identity matrix. That's definitely a unit. Therefore, linearly independent solutions.
Solution set exists.
Fundamental solution sets there. Got it. This is, by the way, the standard proof that there exists a fundamental solution set. This is from Nagelstaff and Snyder. This stuff is all in the theory section of like chapter 9, I think, or they've relegated it to an appendix. I sometimes make more of a book than is actually there because I want to bully undergraduates into thinking that undergraduate courses say more than they actually say. But theorem 3.11, you have an nth order differential equation, continuous coefficient functions, fundamental solution set, connected subset. Then if y solves the homogeneous equation, L of y equals 0, then there exist unique constants, C1 through Cn. Right, such that what? such that nothing. So this is the general solution theorem.
Yeah.
That you pick any solution to your nth order problem. If you already have a fundamental solution set in hand, there is a unique linear combination of that fundamental solution set which will attain your given solution. So this is the usual C1 plus C2 stuff we do in differential equations, right? This is the logical bedrock on which half the course is hanging.
Oh yeah, I guess the character, after you do the characteristic equations, you know that you can either get like the C1e to the RT thing, and that's a general solution, right? So any particular solution. Oh wait, you're saying like a general solution can be combined to get a particular solution?
No. We're looking at the homogeneous problem.
Yeah.
L of y equal to 0. So it's saying any solution to the homogeneous problem, right, can be written as a linear combination of the fundamental solution set. So that's the thing, is once you have an nth order problem, once you find n linearly independent solutions, you're done. Like, you know that is a linear combination of those will build the general solution, right? And I'm using general solution in the logical sense, not in the specific parlance of differential equations, where general solution is often used to mean you've got a homogeneous plus a particular. I'm using the word general in the general usage of the term in English language. All that stuff with particular solutions, there's a version of that in this paper. We'll get to it.
Okay.
So section 4. So here I solve dw dz equal w squared sine z. I separate variables, integrate both sides. That gives me equation 47, which I then expand into real content, real components. Remember, we saw the components of cosine. It turns out that they're cosine and sine over the hyperbolic numbers. We could derive those in the adding angles formulas. But anyway, their equation 49, there's this solution, the real solutions u and v to that differential equation. So those are actually solutions to the system of real PDEs, which is presented in equation 50. Ux is u squared plus v squared sine x cosine y plus 2uv sine y cosine x, and partial derivative with respect to x of v is 2uv sine x cosine y plus u squared times v squared, u squared plus v squared times sine y cosine x. That coupled system of partial differential equations has solution 49, because if you rewrite that system as the original differential equation I stated, you can just solve variables as I did.
How do you u and v separately though? Oh, okay. You said w. If we do not w equal u plus jv.
I rip off its real and imaginary.
Okay. Because I got the w. I was like, okay, and then you. Gotcha.
So let's see here. Example 4.2. I think it's just another one of these. Like d eta do zeta equal to eta. As natural solution, eta equals k to the e zeta. Where here k is a hyperbolic 3 constant. And what does that do? Well, it solves. So first of all, there's two different things that's going on. All right. That solution, eta equals k